So today's video we're going to talk about kinetics. This is part 2 of a multi-part talk on kinetics. You can find the other videos in YouTube. But what we really want to focus on today is talking about the rate expression, how to determine that rate expression, how to know, find the rate constant, and know how that rate constant changes with temperature. So how do you express a reaction rate? We're going to just study this reaction where ethylene reacts with ozone. This is the sort of reaction that happens to cause smog. And it makes a cyclic ether called oxirane and releases oxygen as well. But in order to figure out the rate at which something happens, you need to put a handle on how you're going to monitoring that things are changing. And so if you'll look at this, we're actually monitoring the concentration and molarity of ozone in a given volume. And so it's very small, 3 times 10 to the minus fifth moles per liter. And you start at some concentration. As the reaction proceeds, that ozone goes away because it's being used up in the reaction. So a few things you need to pay attention to. If you were talk about the rate at which it happened, it's just like the rate at which you travel. It's distance divided by time. The rate that we're dealing with here is how much does this molarity change per unit time. That's what rate is. And in this case, we're going to put a negative sign on there, not because the numbers are less than 0, but because this is a reactant, so it's going away. And if you were following the rate at which O2 was being formed, it would be a positive change in the molarity of oxygen over time. Or the formation of oxirane could be a positive. The rate at which ethylene is going away also would be negative. So there's one of the things about rate. We put a sign on it depending on whether it's going away or it's being formed. This would be a representative rate unit, molarity or concentration per unit time. And here's something you need to understand, and this goes back to the last video where we said, look, if there's a lot more of these molecules present, then the odds of this ethylene finding that ozone is high. But if you're using up ozone and ethylene, then the concentration is dropping. So every time the concentration drops, the rate is slowing down because there's less present. So throughout the entire sequence of the reaction, the rate continues to slow down. So it is not a linear expression. Another thing is to understand different types of rate. And much like doing speed or velocity, it has a good analogy. You can always find the average rate. You start at some point, some concentration of ozone, and you end up at the end of the reaction at some concentration of ozone. So that change from this concentration, 3.25 e to the minus fifth, it ended up somewhere around 1.25 e to the minus fifth. And it looks like it took just about a minute to do that. So change in concentration over change in time, that would be an average rate. So what's an instantaneous rate? Well, at each moment in time, there was a rate of decay. At this point, it was the most concentrated, so it was probably the fastest rate of decay. And the way you find that is if you could take the tangent at each of these points. And the tangent, you'll remember from your mathematics, is the line that touches that point without crossing any of the points on either side. So early on, the rate is very fast decay. That's at time 0. Here at time 20 seconds, the rate is slowed down some. And if I wanted to find the instantaneous rate at 40 seconds, I would have to find the tangent at this point. And this is where calculus comes into play because there's formulas that will actually tell you the tangent line at each different point along this changing function. As delta t gets smaller, the average rate starts to approach the instantaneous rate. So one of the things that we understand from calculus is that, look, if this is the large average rate overall, and I can start getting smaller and smaller, in other words, instead of doing the first point and the end point, let's cut it down and do the first and maybe the third point. Or let's cut it down and do the first and the second point. As the time difference over which the average is taken is lower, then you begin to approach the rate at the origin. So the application that we can take to the lab, if we want to get an instantaneous rate or a close to instantaneous rate, we take an average rate with as small as a time interval as possible, and that will be getting closer to the instantaneous rate at the origin. So how do you measure rate? Well, how do you find this change in ozone per unit time? So one of the ways that you measure is spectrophotometric. In other words, you have some sort of excitation source, in this case a light. It passes through the sample, or some of the light's absorbed and you measure how much is transmitted, or you measure how much of the light is missing and record the absorbance. And for this particular reaction, you can do an absorbance of ozone. And here's a spectrum that just shows that at 260 nanometers, there is a peak that is evolved whenever you shine light through ozone. And this is just showing how that concentration drops over time, according to Beer's law, which shows that absorbance is directly related to concentration. Here's another method. Maybe if you had this reaction, so let's look at the species. I've got this covalent compound, T-butyl bromide, water, and you're making T-butyl alcohol and hydrobromic acid. Well, this is not acidic at all, but as you form the products, this is an acid, so you could just watch the pH. And remember, as acid is formed, the pH is going to drop. So here is another example of how you might monitor so you could find the rate at time. So once again, if I took the difference here and correlated pH back to the concentration of H+, but I could do that different in concentration per unit time. That would be an average. Or the smaller I get, or if I wanted to use my calculus, I could use a tangent at any one of these points and have an instantaneous rate at any point. Here's another way. This is hydrogen peroxide, and it's decomposing into water, and oxygen is given off. And if you look when this reaction starts, there in essence isn't anything except water vapor pressure in the headspace. So if we were to put hydrogen peroxide, a solution of that in here, and run this reaction, then I would start to evolve oxygen, and the partial pressure of oxygen would build up, and you could start measuring that with a gas meter. So here's an example of running this reaction, and you see that the pressure in the headspace starts to build up in millimeters of mercury. But once again, as the reaction progresses, the rate at which it evolves slows down, and that's always going to be common in a chemical reaction. So once again, rate is expressed as change in species per change in time. And one of the things to understand is, okay, maybe I can just measure oxygen evolved, but that doesn't mean that I can't then re-express this rate in any of the species in here because of stoichiometry. And that's what this expression does for you. It just basically says, look, no matter what the equation is, if I know the coefficients in front, in this case, small a, small b, or here that's referring to 2 and 2, and the coefficient up here is assumed to be 1, right? I can always express how things are related to each other. Take your change in concentration divided by change in time, and the only thing you have to do is put the coefficient in the denominator. They'll all be set equal to each other, and by convention, remember, if this is a reactant, it's going away, so we put a negative sign on it, and if it's a product, it's being formed, so we put a positive sign on it. So what do we do with this equation? How does that work? For example, if the rate of oxygen production is a change of 0.2 moles per minute, how would you express that same rate for hydrogen peroxide or water? Okay, so here's how we do it for water. We'd set it up and say, okay, we know that we're measuring oxygen production. It's 0.2 moles per minute, so that's right here, it's positive, 0.2 moles per minute. We'll just set it equal to my water production, and the only difference is we're going to solve for this thing, but we need to include that coefficient. And it just goes down there in the denominator. Now it's just math, and let's solve for this piece to know what our new rate is. So you multiply through by 2, and you get the change in water per unit time is 0.4 moles per minute. So that makes sense. If oxygen is evolving at 0.2 moles per minute, then water must be evolving at twice as fast, because the stoichiometry says there's 2 moles for every one of these formed. So now let's set it up for hydrogen peroxide, which has the same coefficient as water, so it's going to have the same rate, only it will have a negative sign since it's a reactant. But how do you have a mathematical expression of the rate law? And here's the reactants and here's the products. The rate law is some combination of the rate, which we just talked about, in some sort of moles per second or moles per minute, something like that, equals the rate constant times the reactants that are involved in the rate, and we usually don't include products in the expression of the rate law. This is rate, this is what we just talked about, and you can express it as any species in the equation. That's what we just did with our last homework examples. K is the rate constant. This is a temperature dependent number, and the units will vary, okay, depending on what goes over here, because these have to cancel in such a way that you end up with basic molarity per unit time. And X and Y are the order. This quantifies the influence that reactants have on rate. So we'll further explain that, but for right now, let's just say it's reactant A is involved. It may have an influence of nothing, so it's a 0 order. Or it might have a larger influence, so it might be a first order, or it might be twice that, so you'd put a 2 in here and say it's second order. But the size of this number tells what the influence of. If it's 0, then it has no influence on the rate. So to help you understand how different reagents can have a different influence on the rate law, I'm going to give you 2 examples. So the reactions are very similar. In the first one, the electrons on this oxygen attack this carbon, and the bromine leaves. And in the second reaction, the electrons in the oxygen attack the carbon and the bromine leaves. Very similar reactions, but slightly different. And they have a different rate. And that's what I want to show to you. And here's what I'd like for you to understand too. These are what's called overall reactions, and they're great for thermodynamics. They're great for doing stoichiometry. But overall reactions don't always give us enough information to figure out the rate law. So let's focus on the first reaction. This is the T-butyl bromide one. The only way we'll know what the rate law is, we have to look at experimental data. So once you get experimental data up, here's what we're doing. We're looking at T-butanol formation. So this is something we could see on a spectrophotometer, for example. As this starts to evolve, it has a different signal than anything else in the reaction. So I can measure how much of this is being formed. So here's what we're going to do. We're going to start with different concentrations of each reagent and look at the instantaneous rate. Then we're going to change the concentrations and look at the rate, change the concentrations and look at the rate. But the key is this. In experiments 1 and 2, we hold T-butyl bromide constant and change just the water and see how it affects the rate. In experiments 1 and 3, we hold water constant and just change the T-butyl bromide and see how it influences the rate. Okay, and then we can determine our rate law. So watch how we do this. And so once again, the rate we're monitoring, this number right here represents the molarity per second that's changing with T-butanol. Based on holding T-butyl bromide constant and doubling water, reactions 1 and 2, this is held constant, we're doubling the water. What happens to the rate? Not a thing. So what does that mean in terms of water? It means it's 0 order. It has no influence on the rate. All right? Based on doubling the T-butyl bromide, right here, while holding the water constant, what happens to the rate? Well, if you took off the e to the 4, that basically doubled the rate, right? So if I double the reactants and it doubles the rate, that's a first order reaction. That means that's raised to the power of 1. All right? So now we're almost there. Now let's find the K. How would I find the K? Well, the key is this. Take the part of the rate equation you've already built, plug and chug any one of the number sets. It doesn't matter which one of these experiments I use. I'm going to use entry 2, for example. And so now I plug in, well, my rate in entry 2 is 4.63 to the 4 equals K. That's what I want to solve for. And in this case, water is 1 and T-butyl bromide is 0.5. I plug and chug, solve for K. The K is 9.26 e to the fourth per second. And I would like for you to now pause the video so you can see your data and try the other two entries, and you'll see that you get the same K even if you'd entered 1 or you had entered 3. So now that you've tested with the other sets, you see it doesn't matter which data set you choose. You just need to plug it in and you can actually solve for the K once you've established what the order is of all the reactants that are involved. And in this case, water doesn't even influence the reaction. And the other thing is, remember, this K is specific for this temperature. As we learned in the last video, if you increase the temperature, generally you're going to speed up the reaction. So now let's talk about this reaction and see why it is that water really doesn't matter. I mean, we go back to this rate law. We see from the experiment it's true, but let's explain that so this starts to make sense to you. Remember, once again, this is the overall equation. All right, and here's the rate law. We just determined it. Now we don't even need to include the water because we know water isn't an influence in the rate. So if you know the original starting concentration of the T-butyl bromide times this constant, at 25, it'll tell you the initial rate of the reaction. And then as that reaction proceeds, this concentration is going to change, but that concentration, the new concentration times this constant will be the new rate, and on and on and on. We describe it as being first order for T-butyl bromide. It's zero order for water because water doesn't influence the rate. And if you add the orders, remember, if you have powers and you add them together, it's first order overall. And this is called the rate constant, and it solves for the rate. The rate constant will have different units depending on what you put in here for the orders. But at the end of the day, the rate constant times these concentrations raised to whichever power will still always pop out a rate with the units of concentration per unit time. So that's real important. So to understand what happens, we're gonna use this reaction diagram. And remember, as you go up on a reaction diagram, you're increasing energy. As you go to the right, it's the progress of the reaction over time. So this is actually a multi-step reaction. In the first step, the T-butyl bromide actually just loses bromine. And what forces that to happen is actually all the size of these steric groups. They force that off of there. And you have this what's called a carbocation. It's a planar carbon with a plus charge. And a lot of times the groups you put on here can also help stabilize this, but that's another story. So we're going to put this on the reaction diagram. And that's, as we've talked about, that's the activation energy to get to the product. Okay, in this case, the product is this carbocation. And in these kind of multi-step reactions, sometimes we call this the product of a multi-step reaction, but sometimes we also refer to it as an intermediate. And an intermediate, by definition, means that you can usually isolate it. Okay? Because it has this little thermodynamic well it can sit in. Okay, here's the second step. Remember the reaction. Water interacts with this, but in reality, what water interacts with is the carbocation. And when it reacts with the carbocation, it goes through this transition state, right, where the electrons on the oxygen attack that positive carbon. And then that hydrogen releases, and you're left with the T-butyl alcohol. But the other product from the bromide ion here and the proton that's released right there are hydrobromic acid. So now if I was to graph this on the reaction diagram, I go over another activation energy hump and get to the final products. This, though, because it's only temporary, is called a transition state. And by definition, what discriminates a transition state from an intermediate is a transition state usually can't be isolated. It's very fleeting. And it sits at the top of this activation energy hump. It's very unstable, very reactive. So the key to this is if you'll study these reaction diagrams. Now, once again, You can't intuitively know just by looking at this, oh wow, that's a multi-step reaction. You don't intuitively know that this second step is has a lower activation energy hump. These sorts of things you do with some different experimentation. Although you did have the clue from the reactions you ran earlier that somehow water wasn't really part of the rate. And now when you look at this energy diagram of all the components, you see that yes, indeed, it's just kind of like driving here. If I had enough energy to get up to the top of this hill and I roll this ball off the hill, it's easily going to flow over this and down to the products. So consequently, this is the slow step. It's what determines the rate. And once you get over that hump, you're always going to get down to the products. The second step is not consequential to the rate at which this reaction happens. So the high activation energy hill represents a slow step, and the low activation energy hill represents a fast step. And when you put them in this order, you're always going to have a rate-dependent step occurring with the slow step. So that was that reaction, and that explains why you come up with this rate equation that does not depend on water. Now here's the second reaction. Let's study this one. Do the same experiment. Now we're going to monitor the methanol formation. Okay? The change in molarity per second of methanol. We're going to do the same experiments where we start with different concentrations of methyl bromide and sodium hydroxide. We'll start where we hold the methyl bromide constant and increase the amount of sodium hydroxide. Now it does seem to change the rate. And then in this reaction, right, we're going to hold sodium hydroxide constant and change the methyl bromide, and it also changes the rate. So just quickly looking at this data, we know that both of these influence the rate. So they both need to be part of the rate law. But let's figure out by how much. So we just rough this out. Remember, once again, what rate means. We're monitoring some change. And as we learned in those first set of slides, if I monitored this change, I could express it in any of these other ones according to that one little equation I showed you. And in this case, they're all 1 to 1 to 1. So whatever rate of change for methanol is the same rate of change for sodium bromide being formed, or it's the same rate of change for sodium hydroxide or methyl bromide going away. Okay? So anyway, that's rate equals the constant times. So let's just deal with the hydroxide first. Based on holding methyl bromide constant and doubling OH entries 1 and 2, okay? That's held constant. Doubling that, the rate actually doubles. 5.35 doubled, right, would be 10.35. And see how it changed the order of magnitude. So when you double the concentration, it doubles the rate, then that's raised to the first power. Now we go down to the next one. Based on doubling methyl bromide and holding sodium hydroxide constant, notice how it also doubles the rate. So in this case, relative to methyl bromide, that also is a first order relationship. Now we can use our little trick again. Now we want to solve for the K. So using the information we have right now, rate, this concentration, that concentration, both raised to the first power, plug in any one of these number sets. And I used entry 2 again. Entry 2 equals K times the concentrations. Solve for K, and it's basically 2.14 e to the minus 2. And look at the units here. Now the units have to be different. Why is that? Well, this is molarity, right? This is molarity, so molarity squared. And if it canceled with that molarity, you'd be left with molarity per second, which is what the rate has to be in. And remember, this K is specific for 55, and that was information there that was given in the experiment. So if the temperature changed, that constant would change. But this particular experiment took place at 55C. All right, so now let's look at what happened reaction mechanism-wise that would explain why this is just second order overall. So here's our expression. First order for methyl bromide, first order for hydroxide. If you add those together, it's going to be second order overall. So here's the actual reaction. It's a one-step reaction. Reactants combine, they go through this intermediate, and boom, you form products. So basically, as hydroxides approaching one side of the carbon, this bond is softening and bromine starting to leave. That's what you call a transition state. When the bromine officially leaves, you're left with methanol and the bromide ions. Okay? So here's our reactants. You go over the activation energy hump, and the size of this determines the rate. Remember, the height of this determines the rate. There is not multiple steps. There's only this fleeting transition state, which you usually can't isolate, but that's changed a lot with some of the ultra-fast laser techniques that have been developed recently. So it's a one-step reaction, so all the reactants are pertinent to how fast this reaction will occur. And that's what our rate expression tells us. And that's what these do for us. They show basically a constant based on a temperature. They show how much each reactant concentration plays into the reaction rate. And the amount of influence that each one of these reactants have will be determined by the exponent up there. All right. So sometimes the exponent is not easy to find by inspection. So the ones we just did were simple. You double it. Okay, the rate doubled. That must be raised to the power of 1. So here's a little math trick to figure out the order. If we can get this form down to this, A equals B to the M, and I want to know the M, my math says take the log of both sides, the log of A and the log of B to the M. Then if you have an exponent raised to the log, it's going to fall out, and you're going to have M by itself, and you isolate the log of A over log of B. So this expression, when you take the log of both sides, can be rewritten as this. And since we know both of these numbers, right, we can solve for M. And just a little note, reaction orders may be positive integers. That's what we've been looking at. They can be 0 when the reactant has no influence on the rate. They can be negative, and that's a unique case. That's basically what you've done is when you've written the rate expression, you've included products in there. So in that case, that could be negative. And it can also be fractions. And fractions are, as it sounds, just a part. In other words, you don't double it and get a double influence. You double it and you get 3/4 of an influence, that sort of thing. And so one other thing I would say about this, when you do a rate expression as well, is I would also say that these always use reactants in the expression. You don't use the products in the expression. Except for that unique case where you have a negative exponent. Nothing that you really need to worry about in general chemistry too. So now we're reacting NO2 gas with carbon monoxide. You're getting NO gas, which is poisonous, and greenhouse carbon dioxide. And the way to do that is from the experimental data. And so now in entry 1 and 2, you hold CO constant, and you quadruple, right? NO2, that's 4 times increase. And this increases 16 times. So let's figure that out. How much influence is that? Here's a way you can do that. And this is what I was showing you to get it down to that expression of A equals B to the M. Okay, we're going to do experiment 1, and we're going to put it underneath experiment 2. And in those cases, because you held CO constant, that CO expression is going to fall out. And once that CO cancels, you're basically looking at this expression. How does the concentration in 1 compared to the concentration in 2 raised to some power to get the change in rate? So here's my A equals B raised to the M. Now I can do this math, right? 16 equals 4 raised to the M. So if I solve for M, it would be 2. And that's great. But now I'm going to do that with the logarithmic expression in case this wasn't real self-explanatory. In other words, it's not always a pretty number. 4 raised to the second power is 16, and that was easy enough. But just to show you how this is done, if you raise both of these to the log, right, you'd have the log of 16 equals anything raised to the power m. If you take the log of it, the m will fall out, and you're left with the log of 4. So now let's just isolate m by moving the log of 4 over. M equals the log of 16 divided by the log of 4. And now all you have to do is plug that in on your calculator and chug, and you would end up with 2. And this will solve for exponents that are more complicated. It's a good trick, and you should practice it and use it in your homework. So now when we get done, we found out that CO doesn't influence the rate of the reaction, but only NO2 does, and it's a second order. So the rate expression is second order overall and second order in respect to NO2 and 0 order in respect to carbon monoxide. And last but not least, let's find the K for this particular temperature. Once again, you could take any line out of here, plug it into this formula you have here, right? And it looks like we're going to use either line 1 or line 3. Either one will work. Plug and chug, solve for K. K is 0.5, and look at the units. It's moles per second to the -1. And if you took moles per second times moles squared, it would cancel out one of the moles and leave you with moles per second for the rate, and that's what you're looking for. So work your way through that. Make sure you pay attention to the units. Okay, last but not least, so what happens if you know a rate constant and then you want to change the temperature? How does this all relate? And this is a derivative of the Arrhenius equation. And you need data from 2 different temperatures. And here's how this works. Here's the derivative that you can use, and you should memorize this equation. And as we looked at earlier, remember the activation energy? Do a reaction graph. Remember when you go from reactants to products over here, that the activation energy is actually related to how fast the reaction happens, and if you lower that activation energy, the reaction will happen faster. If you raise that activation energy, the reaction slows down. So activation energy is directly related to the constants, and this activation energy is the same regardless of what temperature it's taking place at. But as you raise the temperature, basically you're just getting farther up this hill. So if you have it hotter, it's going to be easier to get over this activation energy hump. And if it's cooler, it starts off a little lower. And so this is what Arrhenius figured out, and he related all this together. And pay attention to some of the things in here. R is the universal gas constant. It's 8.314 joules. So that has to be in joules. And activation energy is usually in kilojoules, so make sure these two resolve. You can either convert this to kilojoules or you can convert the activation energy back to joules, whichever works. Notice that the universal gas constant also has K for temperature, so whatever temperature you're given, it has to be in K. And the other thing is this is the natural log. And also pay attention to that little negative sign. Now that negative sign's in place, and if you remember back to the early videos on working with logarithms, if that negative sign was out of there, you could switch T1 and T2. The reason we put the negative sign in is to keep the order the same. So T2 is the temperature at which this K2 applies. T1 is the temperature at which this K1 applies, and we put them in the same order. This comes first, so therefore we made the temperature first. Sometimes you'll see these switched and that negative sign missing. Doesn't matter, just stick with one routine. That's my advice. Okay, so let's apply this. A rate constant of a reaction is 4.7 e to the minus 3 per second at 25 C. And now you know the activation hump is 33.6 kilojoules per mole reaction that you're trying to drive. So first, just for review, I'd like you to just look at the unit of the K and see if you can figure out the order of the reaction. And here's the way to think about it. Whatever that order is, divided by seconds is going to give you the rate. And you know the rate is in moles per second. So consequently, the order must involve just moles. That's a first order reaction. Okay, so now back to the heart of what we're working on. Let's apply this Arrhenius equation and figure out what the K is when you change the temperature. So we use this equation, we plug in everything we know. Okay? So K1 is the one we know. So if we're going to use this for K1, then the temperature we know is T1. But remember, T has to be in Kelvin. The other thing that we know too is R. The R constant is in joules, so I'm going to take this EA and make sure I go ahead and convert it to joules. 33.6 times 10 to the third joules is a kilojoule. All right? Don't forget your negative sign. And then I put in the R constant. It's joules per mole K. So if I put it on the bottom, see, it flips everything up. Look at how my moles cancel, my J's cancel. All that's left is K. Well, that's going to cancel out when I work this little equation. And once again, because this is in K, I have to turn my temperature to K. I'm trying to solve for the K2. So it's the final temperature at 75 C. And now it's just basically, let's collect all this together and solve that math. Log of K2 equals this. Now I have an expression that says, look, I've got the log of this over this equals that. How could I get K2 isolated? Well, raise both sides, natural exponent E. All right? That's going to make this whole expression here fall out. And this can be solved on your calculator. So K2 over 4.7 e to the minus 3 equals this. Solve for K2, and you get about 3.3 e to the minus 2. And just look at this and see if this makes sense. Here's the original rate, constant, at some temperature. And if you're going to actually raise the temperature, you should be increasing the rate. Therefore, the constant should also be increasing. So it's going from e to the minus 3 to e to the minus 2. So that makes sense. The rate is actually increasing. All right, so now let's use the same expression and see if we can solve for the activation energy. And I go ahead and do a little quick review too, where I basically say, look, you got rate constants expressed as liters per mole or moles per liter on the bottom. That's moles on the bottom times second. I wonder what the rate constant is. Well, a liter per mole is a mole to the minus 1. Multiplying that, mole squared, by that should leave the unit for rate. So if I just looked at this, that's a second order overall reaction. Okay, so now let's get down to the business of applying the Arrhenius derived equation. Okay, so back up a little bit. Here it is. We're going to just plug and chug. Only in this case, we're going to rearrange EA and just solve for EA. You don't have to do it this way, but it might be simpler, where mathematically I'm just going to divide out my negative R, divide this over on the other side, and then we're just going to plug and chug. So we isolated EA algebraically, then we're just going to plug and solve. And when you put in all your numbers, once again, you remember that basically the temperatures have to be in K, which they already are. When you do the math here, plug it into your calculator, and you end up with 1.76 times 10 to the 5th joules per mole. The activation energy is usually expressed in kilojoules per mole, so that's a fairly easy conversion of moving the decimal over 3 times. All right, so I hope this has helped you understand kinetics. And there's going to be another video that's going to work on some more kinetics equations that are also available on YouTube.